So in this one, let's spend some time understanding what non-relational databases are. So to be honest, it's a very broad generalization of a huge variety of databases that are not very similar to each other, right? So people think that, hey, all relational databases are similar. That's true. But it does not mean that all non-relational databases are similar. So non-relational databases as a term is referred to classify all the databases that are neither MySQL, Postgres, Oracle types, like that are not SQL databases, which is a non-relational databases, no SQL databases. It comes from that, right? Okay. Now, what makes them interesting? So a lot of people think that non-relational databases scale more than relational databases. It's not completely true. Let me talk about it in detail, right? So non-relational databases, they come in different flavors. But one thing that kind of, and again, very broad generalization, kind of stitches them is they shard out of the box. So they don't work with an assumption that all the data needs to be present in just 1 DB. Like relational databases assumes that that's where you get foreign key checks, cascaded, basic cascades and triggers and whatnot. Non-relational databases, they don't assume that everything would be there in one node. And it gives you out of the box toolings to split it horizontally. That is why it's a very common quote unquote misconception which says that, hey, non-relational databases scale and relational databases don't. You drop, like relational databases gives you those strong guarantees, it gives you constraints, it gives you features, ACID transactions and whatnot. Non-relational databases don't give you those features, which means if you don't use foreign key checks, don't leverage transactions that much, then you can split even horizontally you can split relational databases. Last video we saw what sharding and partitioning was, right? So that's exactly, but non-relational database gives you those toolings out of the box, which is what makes it a little special. It just makes our life a little easier, right? But apart from that, it's not totally true that all non-relational databases are similar, right? So let's talk in this video. Let's talk about 3 different types of NoSQL databases. We'll look at document DBs, we'll look at key value stores, and we'll look at graph DBs. 3 very common databases that you need to know. Everything else is okay. Like there are far more types of non-relational DBs, but covering all of them might not be that interesting. So things that we definitely need, we would definitely go through that. Right? Okay. So let's spend some time understanding what document DBs are. Now, document DBs are closest to relational databases. Now, they are mostly JSON based. Again, it's a crude generalization. Like if you think about it, relational databases, we can say things very confidently because it's a standard. The way you can access relational databases, SQL queries, the way they store data, rows and columns. In non-relational databases, it's not completely true. Right? Because every database is free to choose their own query layer, their own storage layer, their own optimization, their own features, their own guarantees. Right? So that is where it's very difficult to generalize anything when it comes to non-relational databases. So, but let's spend some time understanding document DBs. Document DBs are the closest when it comes to relational databases. They are mostly JSON based. 2 popular examples, MongoDB and Elasticsearch. Right? MongoDB, very famous document database. Same thing goes with Elasticsearch. Elasticsearch, although it's more famous for search use cases, but you can still use it like how you're using MongoDB for that matter. Right? The best part is they support complex queries. Now, what do you mean by complex queries? Complex queries implies aggregations. Complex queries, like in SQL, you can do aggregations. Select start from this, group by this, sum this, and whatnot. All sorts of these features, filters and summations and whatnot, you can do it on relational DB and document DB. Most document DB gives you these features out of the box, which is where I say it's closest when it comes to relational databases. Now, one other key feature of document DBs, which is very similar to relational databases, is partial updates. So what happens is, let's say I have a document, I have user ID and total post. Total post is, let's say, set to 270. For a particular user ID, this is the total post. Whenever I want to do an increment I can just issue a command that says, hey, increment total post equal to total post plus 1 in this particular document. And it would just update this one thing. You'd say, hey, but every database does that. No, every database might not. Partial updates is very important feature for most databases, but a lot of databases, what they ask you to do, they ask you to read the entire thing, update and put the entire document back. Right? Mostly key value store asks you to do that. Again, there is no strict rule, but partial updates is a very good feature for a lot of databases to have, and document databases offer you this feature, which means that you don't have to read the entire document to make one small update. You can just issue that small update as part of your query and your database would apply to that. This makes your database performant. This makes your network IO very minimal because you are just sending. Imagine this document was 1 KB big. You just wanted to do count total post equal to total post plus 1, but you have to read this 1 KB document, update and then write this 1 KB document back. So you're doing 2 KB of data transfer unnecessarily just to update this one integer, right? That's why partial updates is a great feature and most document databases do that. A lot of practical use cases where document databases fit very well is in-app notification service. So for example, on Facebook, on LinkedIn, when you get notifications, you see the list of notifications that you got. I'm not talking about push notifications. I'm talking about in-app notifications that you see by clicking on the bell icon. Those things are very well powered by document database because they are unstructured. You can put any kind of data in there. It does not need to follow a very strict structure as part of it. There's still structure to this, but you can put a lot of ad hoc data into each notification, right? So that's the beauty of it. So in-app notification, best example for that. Another is catalog service. So let's say you're building an e-commerce app. You want to just have a list of all the things that your store is selling, that is catalog. That you can power. So product title, product detail, maybe seller wants to put some additional information. You don't have a particular schema. You still have broad fields that are mandatory, but you still want to support additional fields that your seller want to add to that. Catalog service, another classic example that you can build using document database. Right? Second class of database, really interesting one, are key value store. Key value store are very minimal. They are very minimal in nature. They restrict the access pattern to key value based access, which means you can get a key, put a key, delete a key and whatnot, but you cannot do operations on lot of keys in one thing, right? It's always one single key based operations that you are doing. Examples for that, Redis, DynamoDB, Aerospike, 3 classic databases, great examples for key value store. Now these are extremely simple databases. They have very limited functionality and they are meant to just serve key based access pattern. Now you say because they are so simple, you see that they are very widely adopted, but where you cannot adopt it is where you want complex queries like aggregations. Key value database don't support that. You cannot do iteration over it, aggregation over it and fire complex queries on values. It's all key based. Given the key, do me something. You cannot go within the value and do something around it. Like random attribute from the value you pick and do something. Key value database doesn't support it because then it goes into territory of document based databases. Right? Okay. But because it is limiting its functionality, it's limiting its access to just key based access. What it gives you very high ability to shard and partition the data. This is its biggest feature because now you know that your access is very limited to just key based things. Now what happens is you can literally spin up hundreds of nodes where you're distributing the data and querying it, and you get very large scale in this system without having any hiccups. That's the best part of key value stores, which is where you see key value stores getting very high adoption. And in most cases, so Amazon DynamoDB, when they issued the paper around Dynamo, what they've listed in the first couple of paragraphs is very interesting. That when they analyze, so Amazon was mostly relational database driven. Almost every use case was powered through relational databases. But when they analyzed the kind of queries, the way they were storing the data and accessing the data, they found out they were not really using features of relational databases. It was almost always key-based accesses, quote unquote. Like almost data storing in primary keys, given a primary key, give me the data. At max, one attribute indexed, right? Which is what gives you this idea that, hey, key value store, although they seem very limiting, they're not actually as limiting as you think they are. In most cases, key value databases are just sufficient enough, right? Which is where they see a massive, massive, massive adoption, right? And practical use cases of it. Profile data, given a profile ID, give me the profile information. Given an order ID, give me the order detail. Given an authentication token, give me the authentication object. Given a message ID, give me the message. It's so common. Key value access are so common. And to be honest, most use cases you may think key value is the way to go. Except when you need a lot of complex things out of your database, key value databases shine like anything, which is where DynamoDB is seeing massive, massive, massive adoption. Right? Okay. Now, one thing, if you think about it, designing a key value database is very easy when you do it with relational databases, because relational databases don't prevent you from doing anything. Primary keys becomes the key, value becomes string. Let's say you're storing string against it. You can shard relational databases and whatnot. You can use relational databases and document databases as your key value databases, right? And then key value database is just an access pattern. Some databases, and which is where I say that there is no standardization, right, across non-relational databases. So pick your favorite. So long as you're limiting your access pattern, you get the features that you want, right? Okay. The third kind of database, GraphDB. Now, graph database, why I'd like to talk about graph database is graph databases are very fancy things. Now, whatever you did in your graph data structures, like nodes and edges and vertices and graph algorithms and whatnot, those things, take all of that, bundle it in a database and throw it out. That's exactly what a graph database is, right? So whatever fancy graph algorithm we studied, shortest path, least common ancestor, traversal, graph databases specialize in graph algorithms. So wherever you see a graph use case, then hey, I can model this data in graph format. You go for graph databases. For example, A follows B. You store it in a graph database. Arpit bought an iPad. You store it in a graph database, right? So e-commerce, you can think of modeling a lot of stuff in graph databases as well. But warning, a simple warning that anything that you think can be represented in graph database should not be represented in graph database, because relational databases or normal key value store, they give you very good options. But graph databases, you should use it when you want complex graph algorithms that it would be very difficult for you to build on relational database or key value store or document DBs. That is where you go for graph database. You adopt a graph database because you want graph algorithms, not because you can model the data that way. Because to be honest, looking at anything, you can think I can model it in a graph. It does not mean you should, because graph databases are not optimal for transactions. They are not optimal for iterations. What they are good at is they are good at graph algorithms. So when you need sophisticated graph algorithms and you can model your data in a graph-like way, that's where you go for graph database. Always, always, always remember this, right? And you can use it to power social networks, A follows B, recommendation engine, fraud detection. We will take a look at them in explicit system designs that we cover at the end of this. But yeah, these are fascinating databases. So now, as part of exercise, what I would want all of you to do is I want all of you to, on your local machine, spin up MongoDB, play around with it. Spin up, let's say, spin up Redis, play around with it. Spin up Neo4j, dgraph, pick your favorite graph database, just play around with it. See the kind of features they provide. In a lot of cases, people don't know how to use it. They know what graph databases are, but they don't know how to use it. They don't know the capabilities of those databases, and which is where you just cannot say, hey, I don't know this stuff. Just spend some time exploring those things. It's very fun, and take this as an exercise out of this particular session. Right? So yeah, that's all what I wanted to cover in this one. I hope you found it interesting. I hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks for time.